Good morning, good day, and good evening to all our attendees joining us for today's latest Data Science Central webinar. I'd like to start our event off today by thanking Pivotal for sponsoring today's event. This year, Pivotal will be sponsoring a series of educational webinars in partnership with Data Science Central called the Pivotal Data Labs Webinar Series. Pivotal is simply a wonderful partner and supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. I would also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Splunk, Tableau, Teradata, Actuate, Hortonworks, and Tibco, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you have not had the opportunity to view them, I would encourage you to check them out, as they do provide some very useful information. Today's webinar is entitled Machine Learning for Forensic Accounting. Before we begin, I'd like to just briefly review the format for today's webinar. Today's event will be approximately 1 hour long. We have two panelists that I'll introduce to all of you in just a moment. We should have approximately 15 minutes for Q&A following the presentation, and this webinar is being taped and will be made available later on this afternoon at datasciencecentral.com. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing them and presenting them on your behalf during the Q&A portion of today's event. My name is Tim Madison. I'm one of the co-founders of Data Science Central, and I'll be your host for today's webinar. I'm very pleased to introduce today's panelists, Julia Farinas and Sarah Ernie of Pivotal. Julia is a senior principal data scientist for Pivotal, where she is the lead for the healthcare vertical. She has extensive experience in the application of algorithmic approaches to complex problems in multiple verticals. Before joining Pivotal, she held positions at IBM and mFactor, where she helped her customers make optimal business decisions under uncertainty by marrying machine learning algorithms with optimization routines. She holds a PhD in operations research from the University of Florida. Sarah is a senior data scientist with Pivotal as well, starting at Stanford, where she performed interdisciplinary research at the interface of biomedicine and computer science, specifically machine learning. She focused her efforts on building computational models, enabling research for a broad range of fields in biomedicine. She holds a BS in biology with a specialization in bioinformatics and a minor in French literature from UCSD, and a Master's of Science and PhD in Biomedical Informatics from Stanford University. Welcome to you both, and thank you for taking the time to be with us today. In large businesses, many entities purchase a variety of products from many vendors. In these very complex systems, tracking activity that is typical versus fraudulent or wasteful is made difficult by the large number of transactions that are poorly documented, lack metadata, or have data entry errors. Traditional approaches apply rules to filter and flag transactions that resemble prior fraudulent or wasteful activity. These deterministic methods fail to establish a normal behavior and therefore cannot identify any anomalies. A more sophisticated approach is able to understand baseline behaviors of business units or vendors and detect deviations. This requires the generation of metadata to understand expected behavior, identifying correct data entry errors, and establish similarities and relationships among business units and vendors. In today's webinar, you will learn how we use Levenshtein's distance, Benfords Law, social networking, and behavioral profiling to detect fraudulent activity. So Sarah, I think you're going to get us started off today, so as soon as you're ready, you can proceed.
Great. Thanks, Tim. So my name is Sarah, and I'll be kicking off the presentation today on detecting fraudulent behavior. First, covering today's agenda, we want to give some background on what accounts payable actually is. This is a new field to us as well, and so we want to overview current accounting processes and challenges that we were addressed with in this particular project for which we're presenting results. From there, we want to talk about the types of common accounting fraud and waste. They're prevalent throughout many different industries. Beyond that, what we want to talk about is the meat of this actual presentation, which is complementing these classic rules-based fraud detection methods with machine learning, and we'll be using examples of how we detect falsified invoices using Benfords Law. So rather than deterministic rules, finding a more probabilistic approach to that, and using edit distances to find imperfect matches within those duplicate invoices. Finally, we'll follow it up with very new approaches to fraud detection, looking at vendor networks, looking at how to baseline the characteristics of those transactions for those vendors, understanding similarities between items, particularly looking at item substitutes and how they are purchased. And then finally, profiling purchasing behaviors by business units to understand how they are similar to each other and detecting anomalies. So let's start by overviewing the complexities of the accounting processes that actually leave companies vulnerable to the types of fraud and waste that we observed. So standard accounts payable pipeline is what we're showing here. We start off with a business unit identifying the need for a particular product. Then they identify vendors that are selling those products and they place orders. These may also be services that they need rendered. They receive those products or those services are rendered and the vendors issue invoices. Finally, the company will create a voucher or some sort of internal invoice and actually remit payment to the vendors. Now, there are several challenges based on the complexities of these systems. So when you are, in terms of identifying the product of need, dealing with a large number of items, which could be similar, or many different business units which could be wanting to purchase the same items, you could end up with poor consolidation, so very wasteful behavior of buying either duplicates or not consolidating and buying bulk to actually reduce the overall cost. Multiple business units may have multiple relationships with different vendors. For example, staples can be bought from many different vendors. For this, you do have, again, the missed opportunity for bulk discounts, and you might be purchasing them at a variety of different prices. One vendor may be more expensive. You may be buying them at different unit prices. Receipt of product or service is actually also a challenge because it requires you to track what has happened earlier on in the process of identifying a product needed and understanding whether or not that has been rendered, but also that you may have a recurring service or product that's being rendered. And understanding what the original request was may be difficult. In terms of invoicing, we identified already earlier that we'll be covering duplicate invoices. There is no necessary tracking of whether or not a product is directly associated with a particular invoice, and a vendor can simply send a duplicate invoice. There might be data entry errors where it could be entered multiple times and therefore not confirmed that it's present. We'll cover that as well. Finally, validating any invoice details to being able to go back, make sure that we are following the rules of actually paying the unit prices expected, receiving the quantity expected and not more, is another challenge in this very complex system. Finally, it is difficult to confirm that what you are paying for was actually received, confirm that the payments were sent to the particular vendor, and this is why we'll be discussing vendor networks. There are a lot of complexities with acquisitions of companies, for example. And then finally, duplicate payments can recur for a variety of reasons, but tracking that this payment occurred is actually difficult as well. So for all of this, we'll be covering the different pieces, product substitutes, recurring orders will be covered at some level, multiple business units receiving identical products, alternate vendors, duplicate invoices, and correct payment being remitted. So this is how we'll be following the flow of today's talk. And we'll be kicking it off with Benfords Law.
Now, the first technique that we're going to talk about in this presentation is Benfords Law. Interestingly enough, the most famous name in forensic accounting does not belong to an accountant. Frank Benford was an American physicist, and when he was using a book of logarithmic tables, he noticed something rather peculiar. He noticed that the first pages were worn out more than the rest, leading him to believing in that numbers that started with 1 were looked up more than 2 through 9. So with that idea, he investigated. He collected a lot of interesting data from the nature and recognized this pattern over and over again. There seems to be a specific distribution for the first digits of the numbers, and this law has been used successfully in detecting fraudulent activity, especially if the vendors or the approvers within the company are generating fake numbers. because the way someone would generate a fake number is not going to follow this distribution necessarily, because the intuition says maybe they should be distributed uniformly, for instance, for the very first digits. So there's actually a very interesting website. We wanted to show a few cases, our favorites. So it's called Testing Benfords Law. They collect large data sets to test the Benfords Law on. So you're looking at UK government spending in 2010. The pink triangles show what the Benfords Law estimated the distribution would have been, and the neon yellow bars are the actual observations. You see that it's following it very closely. And populations almost always follow this distribution as well. There are, of course, a few rules when Benfords Law will apply. If the numbers are supposed to be sequential, or they are bounded some way, they're not going to follow this distribution. But and the last one, which is our favorite, is file sizes with the Linux source tree. So it seems very random. You wouldn't expect that to follow the Benfords Law, but actually, when you think about the growth, it makes sense. So the use of it in accounting is very simple. So if you have a lot of payments you received from a vendor, you want to see what the first digit distribution would look like. The distribution on the left would suggest that this is one that will not violate the Benfords Law, but you would look for vendors that would violate, where there's an overrepresentation of higher digits, for instance. But of course, if you work with a large company that deals with large numbers of vendors, you wouldn't want to do this manually, creating all the distributions and then looking at them individually. Rather, you want to come up with a systematic approach. And the customer that really worked this problem with had millions of, actually more than 1 million vendors, and more than tens of thousands of vendors that had multiple transactions. So in order to deal with that, we calculate the Kolmogorov-Smirnov distances from the vendor's first digit distribution to the ideal Benford distribution, and then sorted the vendors based on their Kolmogorov-Smirnov distances to identify the ones that are in violation. That can run in our system within seconds. So it really doesn't require someone to sift through a lot of different visualizations. And not only that, we also wanted to see if anything was sourced from within. So we also did the exact same analysis for the approvers to see what the distribution of first digits were. And in this particular example, actually, no one violated that rule. We also looked at for the vendors that had large Kolmogorov-Smirnov distances. They were a handful, less than 80. And we wanted to see what the distribution of whether certain approvers were overrepresented in the higher digits of those vendors. And for that, we ran a chi-squared model to see if there was some sort of collaboration. And those are the types of things that you can do with Benford. So the second topic that we wanted to talk about, again, we're still in the classical approaches for fraud detection topics, duplicate invoice detection. And the traditional approach is to look at the invoices and capture certain information about them and build some deterministic rules so that you'll see whether there are any duplicates or not. But these rules will rely on, expect that the key information to be exactly the same. So you have the same invoice date, same amount, but different invoice IDs, for instance, which is fine. That is a pool to work off of if you have unlimited resources to check all these potential duplicates. But of course, if you're working for a large company, that's going to generate tens of thousands of duplicates to check manually, which is not practical at all. So we wanted to come up with something that is a little more sophisticated. For that purpose, we decided to featureize the invoices using vendor invoice ID, date, and gross amount. And you see only the 3 dimensions on the right-hand side. And then we decided that we would come up with a good distance measure for each and every dimension and then calculate the distances between invoices. And any two invoice that has a smaller distance than the threshold distance, we wanted to triage that as a potential duplicate. So let's talk a little bit about what those distance metrics would be for each dimension. So you have vendors, invoice IDs, and invoice dates and payments. So vendors we will be addressing in the next section, but invoice IDs, you would want the edit distances to be small for two invoices to be considered close to each other. So that's the one that we're going to address today. For invoice dates, it could be the dates could be identical, the dates could be inverse, or within 7 days of each other. You can come up with similar distance metrics for each dimension. So let's see what we mean by edit distances. So Demerol-Levenstein distance considers two strings and then calculates the number of edits that you need to make, minimum number of edits you need to make in order to get to the second string. So the difference between Levenstein and this extension is that you're also considering transposes. So it will be hard for someone to look and see what the difference is very quickly, but in the way we implemented this function, it's very easy for it to calculate that using dynamic programming, that there is only one change that's made in order to get from string 1 to string 2, and that is transposing 4 and 2. So since we implemented our own functions, of course, we had the luxury of manipulating it to serve our needs. Let's consider this case. We're looking at two different instances. Oops. Let's wait a little bit. So in the first table, you see that there is a 4 inserted in the middle of the invoice ID. So that's, we can consider that an edit distance 1. In the second one, sorry, the string is not in a single row, but the last digits are different, which is like 8 and 9. In the second table, invoice ID, the last digit has changed from one invoice to the next. So it seems like in these two instances, the edit distance should be 1. You need to make just one change in order to get to the other one. But our customer has many vendors that has multiple day, multiple same amount transactions, like some sort of lab testing, etc. So since there's a fixed cost to the service that they're rendering, and they're rendering it many times, it's perfectly possible for them to receive many invoices from a vendor. So we wanted to reduce the number of false positives that we will end up with. So we played with the cost of each edit. So additions and deletions, we said the cost should be low. So if there's that kind of change, we want to consider those invoices similar. High value substitutes and transposers are also considered low cost edits. By high value substitutes, we made certain assumptions, like ones were replaced by I's, zeros replaced by O's. Those are tend to be more problematic than 3 replaced by 6, for instance. That could be that doesn't necessarily indicate a duplication. And then substitutes and last digit substitutes, for instance, we just wanted to read them out. So when you implement your functions, you have the luxury to play with these things in order to reduce the amount of false positives that you will get. So I just wanted to give you a few examples of the types of substitutes we found, since we can't really comment about how much this approach saved for the company and how what the difference was between what this is and the deterministic rules that they had. I just wanted to give you an idea what it could find. So you can see that in the first row you have some high value substitutes. 1 and I's are replaced. It might be a little hard to observe, but that's the idea. And zeros and O's are replaced. Then certain places, a lot of additional zeros, additional 6s, etc., those things. And the threshold something that we parameterize. So you can actually allow the investigators to play with this number and then increase the size of the pool, decrease the size of the pool, depending on what kind of resources they have available to them. So now let's talk about something a little more than what classical forensic accounting does, vendor entity resolution. So when we talk about vendors, so let's talk about why we would need such a thing. For this particular customer, vendors are a very heterogeneous group. They're a healthcare provider, and they also provide healthcare plans. So, which means that they have all kinds of medical services as a vendor, because some of their members who use other out-of-network resources would be need to be paid. Medical device manufacturers, IT services, legal services, pharma companies, pharma distributors, a lot of others. This is such a small list. And so, and the same entity may be represented many times in the system for many legitimate reasons. First of all, there are many mergers and acquisitions. So a company might be doing business with our customer and then maybe acquired by another. Now, those two things should be considered as a single entity, and there is no way for our customer to maintain that kind of relationships. And then there could be many physicians, many contact people from the same vendor. That's a possibility. And maybe you're dealing with different aspects of the business. Maybe a company is providing both products, tangible products and services, and they have different centers, cost centers, and each one has their own ID. But if you wanted to aggregate them and see how much you're paying to this vendor, you would like to be able to associate them to each other. And there are many other reasons, not intentional reasons. First of all, data quality issues. Maybe insufficient search capabilities during vendor initiation will lead them to introduce vendors that already exist in their system. That's one way. And then vendors may also purposefully generate multiple identities with the intention of committing fraud. So how do you deal with that when you don't have metadata that relates all the vendors to each other? So we have a lot of identifiers for vendors. So remit vendor is something that they've been trying to group. There is a little bit of effort there. Metadata that's available. Then TIN numbers. If you don't know, TIN is like a social security number for a company, and sometimes companies do maintain this information for their vendors. Bank accounts, addresses, phone numbers. Two vendors sharing the exact same name and two vendors sharing similar names, then you'll be able to, if you link vendors that share these common identifiers, you quickly start building a network. So not only the ones that are immediately related to you, 1 degree separation vendors that share some sort of common identifiers, but everybody that your neighbors are associated with will also be in the same group, and you can consider these as your vendors. So, so how do you do that? By the way, we talked about similar names, vendors having similar names. So I just wanted to explain what type of work was involved in understanding that similarity. So vendors, of course, all customers have accounts payable systems will have vendor master tables, which would have a single name associated with a vendor ID. But usually the transactional tables also have some sort of name columns in them. And of course, for a single vendor ID, you're going to have a lot of different names. So what we did was we aggregated them and collected it into a document for each vendor. And then we tokenized them. We removed all the stop words, special characters from the names. We processed the synonyms, abbreviations, and then calculated term frequency, inverse document frequencies for each word in each document. And then we calculate the cosine similarities between vendor IDs and determine whether those documents were similar. So this was very successful in catching things like individuals, where sometimes the name is represented as last name, comma, first name, and first name, last name. And a lot of other vendors actually were able to, we were able to identify the similarities between them. So let's go back to the idea of vendor networks again. What do we do with that? So we can have a graphical representation of it. For each vendor ID will be a node, and there will be edges between nodes if they share some sort of identifier. If they have a common identifier, actually there could be multiple edges between vendors because they may share multiple identifiers. So what do you do with this information? We decided that we would run a connected component algorithm. And so this problem is the problem of identifying all the subgraphs where each node in one subgraph there is a node path to another node in the same subgraph. And then, of course, there are naive sequential algorithms available for this problem, and our own data science team actually implemented a very efficient algorithm to run this kind of algorithm in a data parallel computing environment. And it can deal with very large graphs with billions of rows, millions of nodes. So we were able to run this very quickly. So how would you use this for fraud detection? So there are many ways you can use this. First of all, you can take one data source out of the equation and build your graph using all the other identifiers. So then you would have different components, and you can run the component connected components algorithms with the edges where all the information comes from, all the data sources except for the one that you held. Let's say in this instance, bank accounts are not used in building the network. Then now that you have your connected components, you can check bank accounts to see if they connect any components to each other. So this will be successful in identifying bank accounts that are shared by distinct vendors. So there's no reason why these groups, based on all the other identifiers, there's no reason why there should be some sort of connection between these two groups of vendors, and then your analysis can identify that there's something interesting going on. And it actually identified a lot of the data problems. For instance, the phone information was shared among connected components that were seemingly distinct. But then further investigation revealed that sometimes the pharma distributor's phone number was entered as the pharmaceutical company's phone number. So it can be used to help clean the data, but once the data is cleaned, more and more cleaned, the remaining anomalies will lead the company into identifying more fraudulent activities. And then, of course, whenever there is a fraudulent activity, they're never in isolation. You should expect to see a lot more. So we thought that if, with an analysis, you came up with, you want to blacklist the vendor, then let's say this vendor is using a virtual office in a state that they don't operate. And so that may be reason for you to be suspicious of them. Maybe the investigation also confirmed that this is something not quite right. So if that's the case, just instead of stopping there and then blacklisting that vendor, you also want to go through this network and see all the other vendors that are associated with this vendor, not only the first-degree neighbors, but the whole network, and then blacklist the overall network. That will be a way for you to enhance all the other fraud, waste, abuse initiatives. Okay, so let's also talk about behavior profiling for vendors. So in this case, we assume that majority of the transactions that come from a vendor are going to be legitimate, reasonable, normal. The problem is that with vendors, there's not one normal behavior. There could be a lot of different, as we were mentioning. Maybe a company may provide hardware, software, services, and each one of them is going to have a slightly different pattern. In terms of frequency, in terms of amount, in terms of the business units that they deal with, whether the payment methodologies, etc., the addresses that are used. So it's perfectly fine for this. Makes the problem, of course, a little harder. You should expect to see multiple normal behavior from a vendor, but what we're looking for are transactions that do not look like any others. So if the goal is that, you could do featurize all vouchers that come from a vendor, for instance, and then run a clustering algorithm. You start with 2 and then determine the density and cardinality of each cluster, and maybe if you would identify distinct behaviors for them, depending on what kind of features you use. And that's, of course, the hard part, coming up with really meaningful features and normalizing them in a way that will allow you to come up with clusters that will be meaningful. So maybe this analysis will result in some big clusters which will have payments that are more than 100,000, usually with business unit 1, 3, 4, and it could be weekends or weekdays, and the payment methodology is ACH, and the approvers will be these ABCs and all the other users, and the address that they use for receiving the money or for contact is one address. And then you can the red one, you can see that there's not a lot of transactions that look a lot like them, and in fact they're not even close to each other either. So this is everything else. So obviously this is not something that this is something that our investigators should be looking into. So we're showing you a very small instance, and for larger vendors that have thousands and thousands of transactions, of course we use something that will scale a little better, like k-means algorithms, but for smaller vendors it's easier to visualize what it looks like when things are clustered. And you can see that there is a group on the right hand side, that's one behavior. There are other somewhat normal groups, and then one of them doesn't look quite like the other, and then you'll be able to, not all of them of course are going to lead into fraudulent activity detection, but it is a place for the investigators to start investigating.
The last topic we're going to cover today is understanding item purchasing behavior. So we've moved from the approach of looking at entering invoices to understanding vendor behavior, and now we'd like to understand purchasing behavior at the level of items rather than at vendor input. The reason why item purchasing and overall business practices related to that is interesting is that in large organizations, you actually have many different business units that can all purchase their own items. I think an easy example is in an office, you might have different entities that are responsible for different portions of the business. You might have data scientists who are interested in purchasing subscriptions to journals, and you might have people in the marketing team who are interested in purchasing items for distribution. So understanding the similarity in function and therefore expected purchasing behavior, we might be able to pull out business units that are purchasing items outside of what is generally expected. So in a very large organization where you have multiple offices, for example, multiple marketing and data science units, you'll be able to compare those. So really the opportunity we're presented with here is being able to look at every business unit or item and understand whether or not either of these are exhibiting some sort of an anomalous purchasing pattern, so we can understand if there is some sort of fraud being committed in terms of buying items that are not expected or at a volume that isn't expected, or again identifying wasteful behavior where things that could be purchased at a different unit price or from a different vendor might reduce the overall cost. Now, one of the biggest challenges we have is in the presence of substitutes. So substitutes would be an instance where you can purchase one of a variety of items that generally serve the same purpose. So going back to the example of staples, there are many different manufacturers of staples, and at the end of the day, you could use them interchangeably. So in order to solve this problem, to truly identify whether or not business units are making inappropriate purchases or whether or not a particular item could be selected for another substitute, we want to be able to group those items in order to track that sort of behavior. Now, in general, that's a pretty difficult task. And for the particular customer that we're dealing with, we focused on one of the largest spends, which happens to be in terms of item purchases in the pharmaceutical space. Now, in pharmaceuticals, there are a lot of substitutes. That could be because there are multiple types of a particular drug that is created. So they could be similar sort of treatments. Or it could be actually a generic offered in place of a brand name for a particular drug. In general, that would be a pretty hard thing to try and resolve so that I understand that one drug is actually the same as another. We can use things like names. So Julia mentioned earlier actually trying to featureize the description of a vendor's name. So we could use the description of an item in this case as well. But in this case, we actually have availability of external data sources, and something that our team works heavily with when we can identify metadata that is provided to us. The FDA, as a result of this Drug Listing Act of 1972, actually requires any commercially distributed drugs to be updated into this National Drug Code directory. So the NDC is available to us. The NDC contains these unique identifiers for drugs, and it includes information about the manufacturer, the active ingredients, and dosing of the drugs. So you might have multiple types of pills, for example, for any particular active ingredient that you can obtain from multiple manufacturers that all have the same ingredient or are grouped underneath treating the same types of conditions. So something like an antidepressant. Now, we wanted to take advantage of the NDC to first map all of the drugs that are being purchased by business units. So now we can understand at the level of a business unit what the profile is of the types of drugs that they are purchasing. Once we have that information, we can go ahead and create profiles of those purchases so that for each business unit we can understand what the distribution of purchases are for all types of pharmaceutical items at the group level, and use that as a distance metric to compare business units to each other or potentially even drugs to each other. Once we have similarities established, we can use that as a way to detect any sort of anomalies. Since we do have information from the business or from the actual customer about whether or not two units should behave the same way, we can now understand whether or not any similarity or difference that we observe is expected. So what would this look like? Let's take a look here at a few business units 1, 2, and 3, and they are purchasing a set of 3 drugs. We have drug A, which is some sort of a drug that treats disease A, and we have drug B and its generic version. So we can look at the spend profile and see, for example, that the third business unit is spending no money on drug B and instead putting all of its money into generics. What we'll be doing is actually using that information, creating a heat map to be able to visualize the differences between business units. So at the bottom, what we've done is taken the spend of each business unit, since we might have one, for example, large pharmacy that might be contained sort of within a very active hospital ward, or we might have a smaller one that might be in sort of a neighborhood. So what we're interested in is the way that spend is distributed rather than actually looking at the dollar amounts and comparing those to each other. So using this approach, we can look at groups of drugs that belong together, and here we're showing one example of a set of pharmacies that have this set of drugs that are all within the same group. As it turns out, what you can do is take those drugs and separate them by brand name drugs and the different generics. And you can actually try and understand, once the generic comes on the market, how purchasing behavior may change. So what we've done is actually separated out the spend of any particular pharmacy prior to the availability of the generics and then after the availability of those generics. What we're seeing here is that across the different pharmacies, sort of in the center of the diagram, we have a set of pharmacies that have spent a lot of money prior to a generic coming onto the market, and that could be for a variety of reasons. Maybe it's a longer standing pharmacy, or they have slightly different behaviors. what we can see is that there is this cluster of pharmacies behaving a bit differently from the others. So if we actually just want to understand now, current day, after the availability of this generic, what has happened, we can zoom in just on that section and ignore anything that happened prior to the availability of the generics, and now understand how the pharmacies are behaving once that particular generic has come on the market. So here what we can do along the x-axis, we're looking at pharmacies, and they're clustered in some sort of similarity. We can now see that they're sort of separated into groups. So when we look at the generics, we can see that most of the pharmacies are actually spending the majority of their money on generics, which usually would indicate that they are being cost effective and avoiding spending larger amounts of money on name brands. However, what's interesting is looking at the different sets of pharmacies that might be spending a bit differently. So where their overall distribution of spend is actually skewed more toward looking at brand name drugs and selling those. If we actually want to try and understand how different those particular business units are from each other, what we want to do is not just look at one individual drug. That would help us in identifying wasteful behavior. What we actually want to understand is whether or not this is a systematic problem where we have business units that are continuing to spend differently across many different drug types. So here what we've done is taken those different drug spend profiles, again, grouped drugs, and understanding what the purchasing behavior is. And we can compute similarities between two given business units. So here on the X and Y axis, we're looking both at business units, and the colors now are indicating how similar any two business units are to each other in terms of their spending profiles. So green indicates that they have extremely correlated spending profiles, and red indicates no correlation. So one of the things that we're interested in looking at is when something is clustered together. So here we see a couple of indicators of things that are grouped, and they look very similar to each other and not that similar to any other units. What we would like to understand is, firstly, whether or not this is an expected sort of clustering. Should these business units actually appear to look like each other? And the second question is there anything else within this group that has not been included, so business units that are expected to behave the same way but have not been included? So these are two types of anomalies that we'd be able to capture: business units that are behaving differently from a big set, or business units that are behaving similarly to a big set where they're not expected to behave that way. This now allows our team to investigate whether or not there is some sort of systemic problem within the system, or whether or not these individual pharmacies should be behaving a bit differently and alter their spending profile as a result. Finally, in summary, we'd like to go over what we've addressed today and hopefully give you ideas of how to move forward in this space. So again, we covered why fraud in accounting is generally difficult using rules-based approaches. So a lot of the things that we mentioned today would have been missed, mostly due to the fact that fraudulent behavior is intentionally concealed so that rules would not be able to capture them. And statistical models would be able to adapt, identifying any changes and sort of flagging anomalies rather than creating rules that say this is absolute fraud. So in fact, what we're doing is enabling these flags to be present for actual accountants to go in and confirm whether or not any particular piece is actual fraud. So what the statistical technology allowing us to do in terms of anomaly detection is first notice differences in billing patterns from expected patterns, which we covered earlier. Profiling purchasing behaviors of those items, again, to understand whether or not there are deviations in purchasing patterns of expected business units. It actually also enables time series analyses, which we didn't cover today, but that's looking at changes in purchasing, billing, or pricing over time, which might be indicative of something that's changed, allowing us to profile individual vendors, individual business units, or individual item groups as well. Finally, it identifies these opportunities for consolidation or bulk purchasing. When we have items that are spread across many different regions, could we actually have purchased them together? So thanks for your attention, and we'll be taking any questions now.
Great, thanks so much. Great presentation, you guys. So we're going to move into our Q&A portion. Just want to thank our audience for providing some great questions. During the Q&A portion of today's event, you'll see the slide that's currently up provides Julia and Sarah's contact information. So if you have questions that you want to reach out to them directly for following this event, please feel free to do so. So the first question I want to ask today is, You mentioned the importance of metadata. What are some other ways of getting metadata to build item hierarchy, vendor hierarchies, and whatnot? Can you address that a little bit?
Sure. So the example that we gave about metadata and hierarchies was with NDC, and that, of course, is a great opportunity where we have availability of an actual hierarchy for us. And there are several other examples of that, of publicly available sources that you might look to. The FDA actually provides ones for things like food even.
Yeah, and there are other great sources like syndicated data sources like IRI, Nielsen, that will give you some sort of item hierarchies for tangible goods. So that's another way of aggregating data, bringing in external data sources to complement the analysis that you run.
But I guess in terms of building your own sort of organic hierarchy, I think a good example is what we were doing with the vendor networks, where you're actually looking at ways of establishing similarities, and that could be through a fuzzy matching approach of descriptions that you might have available. One thing we didn't cover was how you can use a description of the items. We sort of touched upon it. But again, using similar ideas of how frequent a term is and whether or not it's present. Using similarity of profiling purchasing behaviors to try and understand when things can get clustered. At the end of the day, it does require some amount of manual effort to be able to confirm that what you're doing is actually building a very clean hierarchy, something that would approach NDC or Nielsen.
Very good. Okay, great answer. The other question is, what are similar substantial analysis in other functional areas that can be done using Pivotal?
Well, Pivotal has a big data science team. We have 35 data scientists, and we have a lot of different focuses in a lot of different verticals. Healthcare and life sciences is something Sarah and I find interesting. Security, retail, marketing, utilities, all the others. And some of the techniques that we described in this presentation are used in a lot of different contexts also. But I think, does that answer the question?
Yeah, I think so. I mean, I think you did a good job there. Next question is, even with exact matching, you might end up with a lot of duplicate candidates. With fuzzy matching, you expect that number to increase even more. So what are you? So it says what you are doing here is basically prioritizing based on edit distance. Does that make sense to you?
Absolutely, it does make sense. Yes, the idea is not to generate even a bigger pool. The idea is to prioritize the ones that have small distances, so that they'll be if the investigators have limited resources and they can only investigate 2,000, they would go after the ones that had the highest potential to turn out to be duplicates. So it is some sort of prioritization exercise. That is a good question. Thank you.
I think it's also, in general, something that we focus heavily on, not just in the example of fuzzy matching, but across the board in other fraud, waste, and abuse projects, and even other parts of this particular project, where the goal is not necessarily to come up with a bunch of matches and have you go through every single one to understand what's wrong, potentially fraudulent, wasteful behavior, but instead find a way to prioritize based on similarity or likelihood of fraud, but also in terms of bang for your buck, what is actually a large volume fraud versus $20 might be difficult. So coming up with clever prioritizations and confidence in whether or not you believe something is worthy of your attention in terms of likely fraud are both things that we think about in designing any sort of output from our approaches.
That's an excellent point.
Very good. Next question is, you mentioned time series in your last slide. How would you do time series type analysis in this case?
So I think we sort of, very briefly mentioned. I think an easy way to discuss it is item purchasing. So something like a generic coming online was a good example of something we would see where you have a baseline history. So you can look for any particular item across the different business units, what amounts have been purchased. And you'll have regular purchasing intervals. You can understand whether or not those intervals have changed by establishing what normal or baseline purchasing behavior was for a prior year, for example, and then understand whether or not you are well outside of sort of the normal or expected range that you've observed up until this point. You can look at things like...
At the vendor level, a lot of the time series analysis would make a lot of sense if you have some sort of aggregating vendors based on the types of services that they provide to you. For instance, UPS and FedEx. Even though they may belong in different connected components, there's no connection there. But if you have some sort of metadata that says these two companies are providing similar services, then you'll be able to create time series that shows how much money you're spending on packages delivery kind of by business, by geography, and look for anomalies. If there's a sudden increase in consumption, is that justified? Is there a reason for it? So all that kind of analysis, of course, could be made possible if you can relate objects to each other. So at the very lowest level, vendor ID, it's not going to make too much sense because you may observe a lot of anomalies because they may have switched from one server to the other. So this is why building meaningful, good metadata is so important. It makes the rest of the job much easier.
Very good. Another question is specifically by the viewer is in clustering, and they'd like to know if you're using k-means.
So we used a lot of different clustering algorithms in this project because with fraud, there are no labeled data, so you have to rely on unsupervised methods. So for the vendor baselining, for visualization purposes, we showed hierarchical clustering, but of course, we have a lot of large vendors with many transactions with our customers, so k-means made a lot more sense, and it's an algorithm that's available in MadLib, our own open source library for machine learning algorithms, so we wanted to take advantage of that. We did use k-means, hierarchical clustering, and
other people on the team have used like kitty trees, other types of approaches as well.
Okay, very good. So the next question is, fraudsters may try to use very similar data from real data, but innocent errors may generate similar results. How do you separate the innocent from the fraudulent errors?
The thing is, you probably can't. So one shouldn't expect a perfectly clean data to start an analysis. This is going to have all kinds of data entry problems. And analysis will highlight this. This is anomalous. They can't really, the machine learning part cannot really assign intention or the source. So if once those things are identified as anomalies, then if it is a data problem, it needs to be fixed. And if it is actual fraud, then it could be investigated further or taken care of. So yeah, that is a challenge, of course, but we feel that when data is not 100% clean, you don't have very rigid business processes that is followed, your vendor group is very heterogeneous, so there won't be a uniform set of rules that could be applied to each and every vendor, then the machine learning type of approach is the best. Some sort of stochastic approach. Perfect.
You do have those that try to get around the system. I think this next question weaves nicely into your answer there. The viewer said, in my company, data cleanliness and completeness and the lack of standardized business processes are a big challenge. Do you think my company can benefit from a machine learning type analysis for fraud detection, or do we need to wait for our data to be cleansed and processed to become more rigid?
Yeah, I guess I answered that question already. Yes, when data is not clean, this is the only way you can go about. Then if you try to build the deterministic rules, it's going to fail a lot, and you won't have opportunities to investigate each and every instance. Instead, if you consider stochastic approaches, then it will be possible for you to understand the data entry problem. So it will be cooked into the model and anything above. So if an approval is usually skipped for something, instead of that being highlighted as there's a problem here, there's a problem here, you would understand that for this vendor, there are certain exceptions that are made, and it is perfectly okay. So we do feel that you don't really need to have clean data to start using machine learning algorithms.
Yeah, in fact, we can't think of a project that we've been on that hasn't had a data cleansing step. And
no such thing.
Generally, that's where the majority of your effort is spent.
Okay, sounds good. Next question is, how much fraud did you identify in the project, and what did the customer ultimately do with those results?
So we can't, of course, tell you how much we have detected. There are some of the instances that we identified are still being investigated. So we can't give you a number, but we can tell you that they are hiring a data scientist. So they believe in the approach. They want to continue doing similar analysis. That should say something about the success of the project.
Okay. The other question is, let's see, how long was this project and what technology did you use in your analysis? And part of this question is also, how big was the ultimate data set?
So it was a 6-week project that we were working on. And we're dealing with a couple of terabytes of data. I think Julia mentioned millions of vendors.
Hundreds of millions of transactions.
Lots of money. And we did work in Pivotal in terms of staging the data, loading it. A lot of our analyses are actually run there. The cleansing steps that we were discussing would all be run in sort of this environment in Hawk, which is running on top of Hadoop. It has essentially like a database, so you get to interact with it. But
you can build user-defined functions, so all the distance-related discussions that we had in this presentation, for instance, they're directly implemented in the Pivotal environment.
So computing distances would be done using a SQL-like interface. A lot of the other pieces, although we had k-means clustering available, which we ran in the database for another approach for identifying item similarity, once we had grouped items, we ran a lot of our analyses in R, for example. So running hierarchical clustering can be done in R. In fact, you could create lots of different smaller hierarchical clustering models for example, the different vendors by having functions available as well. But we sort of stuck with Hawk and R in this particular instance.
Okay, excellent. Next question is, do you use machine learning to monitor important financial ratios used for fraud detection, or does this occur through the record attributes?
So I think this is limited to this particular project. That wasn't something that we were addressing. So I don't think we can answer in terms of what the customer is doing either.
All right, well, that person can reach out to you directly and maybe provide a little more detail what they're looking for. We have time for just a few more questions, so let me ask this next one. How much data do you need to use some of these statistical models? Do you need to look at history and previous years, et cetera? What's sort of the base to start?
Any baselining approach will require some history, but you don't want too long history, especially if the business is changing, practices are changing, etc. Too old data is going to be very irrelevant. The prices will be completely different. Some of the products that you are attaining now, the standard of care might change for a hospital, for instance. So you're not going to find a lot of valuable information in data that is too old. But of course, you need to have a year or 2 years of data to establish what is normal, what is my baseline, especially for all the geographies. The more data you have, the better. Then you'll have you'll have things to compare to each other. Like if things are happening in a certain way in the south, you would expect the same from the north. So you really need a lot of data, and you also need some sort of distributed computing environment so that you'll be able to run these analyses in a very quickly manner.
Okay, very good. Well, unfortunately, we're just about out of time, so I'm going to have to let that be the last question. But thank you to our audience. We had an awful lot of questions that did come in during the presentation and just now during the Q&A. So I want to make sure that everybody is rest assured that the questions are all going to be sent to Pivotal, Julia, and Sarah, and they can respond to you directly. And again, you can reach out to them directly as well if you have questions following today's event. I do have just a few quick announcements to make. Please mark your calendars for March 4th and our next Data Science Central webinar, which is the 7 lessons from the pioneers of data visualization, sponsored by Tableau Software. Also, as I mentioned, this event is being taped and will be made available later on this afternoon, and you can find it on the home page of Data Science Central in the video section. This brings today's webinar to a close. I would like to thank our audience again for some great questions, and a special thank you to Pivotal as well as Julia and Sarah for their sponsorship and insight into today's topic. My name is Tim Madison. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on March 4th. Good day.